Right, morning folks. Weather's not so nice today, so I'm indoors. Right, we've been looking recently at resistors and what resistance is. So resistance is the slowing down of current in a circuit, and there's different types of resistors. Now we've looked at a normal resistor and we've looked at variable resistors, and we've plotted a graph, or you plotted a graph, of voltage versus current, because this looks at something called Ohm's law. Ohm's law suggests that resistance is current is the voltage divided by the current. Okay, so resistance is the slowing down of electrons in the circuit, and we've looked at how that works in a normal resistor. We've looked at how that works in a bulb. So today's a bit of revision of that, but mainly we're going to look at two specific types of resistor. So let's start off really. A little bit of a starting point is just looking at the different types of resistors. So what resistors do we have? The first one is the one that you will use at home quite a lot, and that one is a fuse. What is a fuse? A fuse is something that is designed to burn out to prevent electrical surges. So that fuse there is a small device. It's a little bit of wire which basically gets hot as too much current goes through it, and that causes it to melt. So that's rated at 5 amps. So if you put that into your plug and the too much current goes through it, then that will melt the wire and it will break. So that's designed to protect your expensive electrical devices from electrical faults. So that's a type of resistor. This next one here is one we're going to look at today. It's called a thermistor, and we're going to look at how the resistance changes as opposed to temperature. But this is quite useful. Thermistors are used in fire alarms. They're used in electrical thermometers. So if the resistance, if the temperature gets too high, the resistance changes. That can set off a fire alarm, for example. We'll look at that in more detail in a bit, and you've got a worksheet with that on. Right, this is a standard resistor. This is a fixed resistor. We would call this an ohmic resistor because it obeys Ohm's law. If you plot a voltage current graph, you'll see a nice straight line going through the origin. If you get a nice straight line on a graph of potential difference of voltage versus current, that's an ohmic resistor. And the little bands on that, which you don't have to learn anymore, tell you what the resistance is. So very important. People who do electronics will put these in circuits to protect various components at different points. Right, this bit of kit here looks like a resistor. You see they've all got the same rectangular shape, but this one's got an arrow on it. And the reason it's got an arrow on it is because you can imagine that being a dial that you can turn up or down. That's a variable resistor, aka a rheostat. And we've looked at the required practical for this, where you change the length of the wire, and when you change the length of the wire, the resistance changes. The longer the length of the wire, the greater the resistance. So this is quite useful. We can use this for volume controls in TVs. But this is how toasters have a cooking time on them. So you can adjust the cooking time on a toaster, or you can adjust the brightness of a bulb, for instance, in a dimmer switch using this bit of kit here. Right, this is the second one of the ones we're going to look at today. This is a light-dependent resistor. So you can see sort of the resistor shape, and the way I remember it is it's arrows going into it. Looks like light coming in and hitting it, and that's what a light-dependent resistor is. And we use that in things like in cameras, so we can automatically measure the shutter speed and all the rest of it. So if you think about your phones, they automatically have flash on them when they need to. That's controlled by things like LDRs, light-dependent resistors. The final one, which I'm not going to mention beyond this, is called a diode. Now, a diode is a one-way resistor. You can see that there's an arrow there going sort of from left to right, and that is the direction the current will go through. Current going backwards will stop. So a diode only allows current through in one way, and we use these things quite a lot. A light emitting diode is one of these, but that gives out light. And LEDs are incredibly good because they use very little energy to chuck out a huge amount of light. So very important bits of kit. Right, so starting point for you guys on your sheet. You have got a series of circuits symbols, and I want you to match them up. So if you pause the video and have a quick look and have a go at that, that'd be great. I'm going to reveal the answers in 3, 2, 1, and there you go. Okay, check your answers and move on. Right, so what are we moving on to next? We're going to look at some graphs, because these are the sort of things we get asked at here. And again, if you pause it and have a look, so how's the resistance of a resistor compared to that of a bulb? Right, which resistor, A or B, has the highest resistance? Well, if you look at the two of them, this is the voltage, this is the push, this is the current, this is the flow. And this, if you look at B needs a very high push, quite a low current. That means I'm having to push quite hard to push those electrons through it. So B is a much higher resistance than A, because A has a large current for quite a low voltage. And if you think about Ohm's law, the resistance is the voltage divided by the current. So you're dividing a sort of big number by a small number. That's going to give you a bigger number than this one, where you're dividing a small number by a big number. So B is the highest resistance, or A is the lowest resistance. Okay. Right, so let's look at LDRs, or light-dependent resistors and thermistors. And what I want you to be able to do is know how we do it, which we would do practically normally. Unfortunately, we can't. And to investigate how the resistance is affected by temperature and how the resistance is affected by light intensity. So, those are the two symbols there. The one on the right is the light-dependent resistor. How do we know? You can see the light coming into it. The one on the left is still got the resistor symbol, but this time it's got sort of this line going through it. I think of that as like a thermometer or a temperature probe. That's how I remember it. It's not the easiest one to remember, that one. So, what do we do? If we want to measure the resistance of a thermistor, what do? You put your thermistor into hot water and you measure the resistance. Then you add small amounts of cold water and you change the temperature and you record that, the temperature versus the resistance. And if you plot a graph of that, this is what you get. So what does this graph tell us? So that's the question I'm asking you. Describe in as much detail as you can how temperature affects the resistance of a thermistor. So pause the video, have a think, tell me what you see. Okay, answer time, right? Let's have a look. So let's see how we're going to get marks in the exam for this. So really at a very, very simple level, and it says grade D to A, realistically it's probably, levels 3 to 5, level 3 to 6. You can see that at low temperatures you've got a very high resistance, at high temperatures you've got a very low resistance. What that tells us is that the resistance gets less as the temperature increases. Right, that's a good starting point. But in more detail, you can see the line of best fit is a curve. It's not linear. Okay, so that means that not only does the resistance change, but the way the resistance changes. So at low temperatures, you've got a very high resistance. At high temperatures, it drops right down. This has got a steep gradient here, whereas here it's much, much more shallow. So you're not asked to explain why, but if you're asked to explain what the graph looks like or describe the graph, that's what you need to get in. Okay, the resistance decreases as the temperature goes up, but not in a linear way. The line of best fit is a curve. So at the start, at low temperatures, the resistance is very high. At high temperatures, it's very low. And the gradient is steep at the beginning and is much shallower at the end. Right, that's a great way to get lots of marks in the exam. So that's what we see with a thermistor. Because the resistance isn't constant, this is a non-ohmic resistor. If you don't get a straight line, it's a non-ohmic resistor because the resistance changes, which a normal resistor wouldn't do. Right, what about a light-dependent resistor then? So we could do exactly the same experiment, but this time measuring resistance versus light intensity. So you could either have a bulb next to the LDR and change the current, or you could just have a bulb and move it different distances away. That would work quite nicely, but a light-dependent resistor. So again, look at the graph, describe as much detail as you can. Again, pause it, have a go, and I'll go through the answers in a second. So 3, 2, 1. Right, so let's have a quick look then. Well, it's the same as the other one, isn't it? The resistance gets less as light intensity increases. Yep. It's not a curve, it's a curve, it's not a straight line. This is a non-ohmic resistor. The resistance isn't constant at different voltages. So for more marks, what can we say? We can say at low light intensity, the resistance is very high, and it drops off to virtually nothing at high intensity, and the gradient at the start is steep, and the gradient is shallow at the end. They're exactly the same shape graph. So at high temperatures, thermistors are very low resistance. At high light intensity, light-dependent resistors are very low resistance. So let's compare that to another non-ohmic resistor, and that's a bulb. Now, we looked at this in quite a lot of detail the other day, and it was the questions from you, what you did yesterday. But let's have a quick look at this. How do bulbs work? Well, we've already looked at this idea that as the temperature increases for a wire, the resistance increases because the electrons are vibrating around much more, and that slows down the movement. So as the voltage goes up here, the resistance increases. You can see that at the start, that as the voltage goes up, the current goes up in a straight line. So at this point, this is ohmic. This is obeying Ohm's law, because voltage and current are directly proportional. But then it starts to curve off, and a huge increase in voltage does not increase the current very much. Why? Because the bulb is increasing its resistance, and it gets really hot doing that. And as it gets really hot doing that, it glows hot, and that's where the light comes from. You've actually got a piece of metal glowing white hot. So what happens to the current of the bulb as the voltage increases? Well, the current starts to go up in a straight line, and then the current decreases. So the gradient is the resistance. So we can calculate the resistance of this. But what that tells us is it's non-ohmic. At high temperatures, the resistance massively increases. So it's a non-ohmic resistor. Okay, so that's the last thing for us to do. At the very bottom here, there's some true or false statements. So I apologise, it's not that. There are some statements here that are for different types of resistor. So what would you use those different types of resistor for? So don't forget, a diode is a resistor that only works in one direction. An LDR is a light dependent resistor, and a thermistor is to do with temperature. So have a go at those. Again, pause the video, have a think, and I will give you the answers in a second. So 3, 2, 1. There you go. And that makes sense, doesn't it? Okay, light sensor, you want a light dependent resistor. A temperature sensor, you want a thermistor. A resistor that has a high resistance in one direction, diode. A resistor for a thermostat, the thing that controls the temperature at home, that's a thermistor. A resistor can be used to control the direction, that's a diode, because it can only allow things through one way. And a darkness detector, that would be an LDR. Okay, hopefully that's made this a little bit easier to do. It is very difficult to learn anything to do with the resistance when you can't do it practically, but we're hopefully getting there. So any questions, please give us a shout. Otherwise, make sure you filled in the sheet and hang on to that for your notes. And I will see you all soon. Take care.